The next item on our agenda is a report to council of Burbank Water and Power, record of reliability through predictive analytics. Please come forward.
Good evening, Honorable Mayor, members of the council, members of the staff, and members of the community of Burbank. My name is Calvin Clark. I'm with the Burbank Water and Power, and I'm an engineer over there. And I know predictive analytics doesn't sound like the most interesting thing at this late hour, but I promise it is.
We've been waiting all night for it.
I know. We could pull up the PowerPoint. What I want to do today is share a story at BWP about how we're changing the game in our industry through the use of a new software tool that we've implemented that allows us to use predictive analytics to improve the quality of service we're providing our customers, as well as improve the reliability of our system. So what I'm going to go over today, I'll talk about our aging electric system and the challenges associated with maintaining such a system, what we've done in the past, and what we're doing today with this new software solution. So you've probably seen this image before. If you drive down Olive Avenue and you're going over the bridge, you look toward BWP, you see that iconic Burbank sign. And that's actually sandwiched right in between our two olive power plants. And I show you this picture because it was taken back in the 1950s. And that's to say that we're an old utility. We're over 100 years old. And with that age comes a lot of maintenance challenges. Our assets and equipment have a typical lifetime between 30 and 80 years, which means our industry is very capital intensive. And while we can't stop the aging, what we try to do with our equipment and assets is to make sure we're aging gracefully. Now, there's many challenges that come along with that. Governmental and legislative mandates challenge us every day as a utility to balance two things, and that's to maintain our reliability, of course, and which means keeping the lights on, and when we do have an outage, to make sure it's as short as possible. And we're challenged to balance that with, of course, managing our costs. Fortunately, in Burbank, we have a pretty good track record. This graph, I know it's really small, but what you're looking at is a national survey done by the PA Consulting Group in 2013, and this we took a survey of over 200 utilities in the nation, and it measures a reliability index called the System Average Interruption Duration Indice, and we call it SAIDI for short. Basically what that means is when the lights go out, how long are they going out for? The national average, that red line you can see on the graph, is 130 minutes. Now, where does Burbank fare on here? Well, we're way on the right side, which is the good side of the graph. And we're actually number 3 on this list. So when we have an outage, our customers are seeing it for about 16 minutes. And that's something to be very proud of in the city. It means in the nation, we boast one of the most reliable systems out there. Now, another way to look at reliability is the average number of outages per year, and this is how we stack up amongst our Southern California neighbors. And we're at the top of this list again. And most utilities measure this in outages per year. We're measuring years per outage. With 0.20, that means on average our customers will see an outage once every 5 years. And it's no mistake we got here. We've made sure every year to build our system strong, build it secure, and making sure it's built to last. Now, on the affordability side, we're not at the top of the list, but we're pretty close. And the reason I'm showing you all these stats is because we're doing a pretty good job in Burbank at balancing those two things, maintaining reliability and managing our costs. So in the beginning, I talked about an aging distribution system, and I'm not trying to single us out. This is something that utilities across the nation have to deal with. The question we ask ourselves is, what do we do about it today? Now, we have a lot of parts and pieces in our system. That bucket-looking device there on the pole is a distribution transformer. And the basic function of that piece of equipment is to transform all the energy that flows through the lines down to a usable voltage that you get in your power outlets. You can plug your phones in, your TVs, or keep your houses cool during the summer. And since every customer and business is connected to one of these, it makes it a crucial piece of our system that we want to make sure we keep an eye on. Now, in the electric industry, there's two major problems we have with these pieces of equipment. One, that it's underloaded or underutilized. And that might not seem like a problem, but an underutilized transformer is wasting energy every day. And over the lifetime of that transformer, that's a lot of wasted costs that we don't want to incur as a utility. The other big problem is an overloaded transformer, one that's pushed beyond its limits. And the reason that's a problem is because it increases that risk of failure that could cause outages for our customers. In the utility industry, we want our transformers to be sized just right. And that's a tall order. And what I want to do now is take you through our journey to finding out how to figure out how to make sure our transformers are sized just right. So I'll talk about how we've done it in the past, our old ways, and how we did some research and development to look into data analytics in-house, and eventually how we justified a full software solution to do this for us. So the old way. Now every utility in the nation, they have some form of this technique, which is how do we figure out how stressed our transformers are. And really the only data points we have to go off of is the monthly reads on our meters. Now, if we know what meters are connected to what transformer, we can input all that data in the spreadsheet, and we get a percentage value. Now, this in no way is exact, but it gets us in the ballpark. And it's really the only way we could estimate. It's our best educated guess of how loaded this transformer was. I mean, if you only have one data point per month, imagine, I mean, energy fluctuates wildly from day to day. So we had no way of knowing at what hour of the day or what day of the week our transformer was performing poorly. And that's where we sought out to find that information, to find that data. And we knew there was one place we could find it with our most recent installation was our AMI network, our advanced metering infrastructure. Now the diagram you're looking at up here is what comprises our AMI network. On the left you see our AMI meters that are installed at every business and every residence. And what these meters do is they collect that data. They collect two things, energy usage as well as voltage. And once a day, it takes all that information and sends it through our communication network in the city and eventually back to our database here at BWP, where we can sort it and analyze it. Now, what do we do with all that data? Well, first obvious answer is for billing purposes, of course. But on top of that, we are able to give our customers access to information like this. What you're looking at is a typical energy usage report that our customers could log on their web portals and have access to. And before we just had that monthly read and told our customers how much energy they use that month, now we can give them information at a much more granular level. They can look at a day's worth of energy usage, which is what that graph is showing, and they can see at what hours of the day they're using the most energy. And this really allows our customers to have the option to make more energy efficient choices throughout the day. Now, we knew we were already getting all this data, so we thought about our transformers again. Well, what could we do with this same data that we're already collecting? And we started off with one simple concept. So I'll illustrate it for you here. Take your typical residential property line in Burbank. It's got power running down the back and a single transformer that connects all 12 of these houses up to power. Now, we knew that since we've had all those meters at these locations and they're all collecting that data for us, there's no reason we couldn't add all that data up and get the same granularity, but just at the transformer level. So we took that concept and we ran with it. And then thus was born Spreadsheet 2.0, which is, I'm not going to explain. I know you can't really read it, but I just want you to know there's a lot more going on in this one than the first one, obviously. And there's one main reason for that. Before, our customers had 12 data points a year, that one read a month. Now that we're collecting data every 15 minutes, what that equates to per customer is 4 data points per hour, or about 35,000 data points per year. Now imagine 12 customers on a transformer, that's a lot of data we're crunching. But with all that data, we can do some pretty interesting things. One, for the first time, we could actually see what our load on our transformer looks like. And you know, I mentioned before we had the two main problems, an underloaded transformer or an overloaded one. Well, now visually we can make that determination. So let's say that green line up there represents your capacity on your transformer. Well, since that graph never really touches that, I would say it's probably an underloaded transformer. Conversely, if that red line represented your capacity, and you could see that it consistently goes over that line, and in some cases almost twice as much, and I would say that's probably an overloaded transformer. And as great as it was to see this information, you notice I've been saying probably, and that's because it still was kind of an estimation. Just to visually make the determination was not being objective with the data we're using. And that's really where we decided to do some more research. We went back to the lab. And that's where we came across this set of equations called the loss of life calculations. I promise I will not bore you with the calculus. But basically what this allowed us to do was to calculate, based on how stressed this transformer was, we could calculate how fast it's aging and how fast it's degrading. So for every one of those 15-minute intervals, we could not only calculate how much load's on the transformer, but we could calculate how hot it's getting. And more importantly, we could predict, or we could calculate how much life and how fast that's degrading, how fast the transformer is actually degrading at each interval. So what that means really is, let's say your transformer's got a typical life of 180,000 hours. That's pretty industry standard for these. And based on all this load you collected, the data, you're calculating that it's losing about 5,000 hours per year. That means for the first time ever, as a utility, we could predict how long these transformers would live. And that's information that, to my knowledge, I don't know any utility is able to do for our distribution transformers. But understanding that value, we still needed one more piece of the puzzle, and that's, of course, cost. That's the most objective way to be with it.
Can I ask just one question? On that slide where it says transformer life, 180,000 hours, loss of life per year. How do you determine loss of life? What is your definition of loss of life?
So inside a transformer, there's insulation paper. And basically, the harder that paper gets, the more it degrades. And the heat is purely based on how much load it's serving. So the more load you serve, the faster it degrades. And so in 1 minute, you could lose. You
have a rate of decay. You know
exactly.
how much heat over how much time causes
exactly.
it to. Okay.
And we can calculate it exactly.
And there are different qualities of transformers, I guess.
Mm-hmm. And they each have their own properties that we factor in.
Thanks.
Mm-hmm. So total owning cost. Basically what this equation allows us to do is calculate from cradle to grave. So from the time we put it up, how much it costs for labor, material, and then for the entire life of the transformer, factoring in electrical losses, all those things, until it's taken down, how much is that going to cost us? We can calculate it with this equation. So knowing the lifespan and being able to calculate the cost, what we can do is annualize that cost over the lifetime of the transformer. And that's really where it becomes the most meaningful to us. It's the variable we call the total owning cost per year. And this is the capstone of all our research because of one main reason is now when we have a load we have to serve and we're given the choice of these 4 transformer sizes, let's say, given all that load that we've been able to calculate, we can now predict how long each of those sizes would live. And on top of that, more importantly, we can choose the most economical size for that transformer for each year it's up there. And that's information that really we'd never been able to do before. This is how we are able to size our transformers just right now. It's not guessing anymore. It's being as objective as possible with all this extra data we're able to get. So understanding that value, we realized it was unrealistic to have engineers just crunch numbers in spreadsheets all day. That's a lot of labor cost. So we sought out a software solution to help us do this and automate the process. And that's where we met a startup company out of North Carolina called Trilliant. And they were doing the data analytics piece of all this stuff for utilities. And we met with them at a conference, and we brought all that research that we'd done as a utility, and even to them, they were telling us that they'd never seen any utility in the nation use the data this way. And realizing the value in that, we decided to partner on this and build a software together. And we had a low-cost solution. They let us build the software for $70,000, which is very low cost in the software world and in the utility industry. But to build the software, we did have to have 2 important pieces, and one of them I mentioned our AMI network, our Advanced Metering Infrastructure. And that was important because we had to have a way to collect all the data so that it could speak to the software. But the other crucial piece of it was our geographic information system, our mapping system, how we map our entire electric system out. That's important for 2 reasons. One, we need to be able to visualize it in the software so it's very user-friendly. And the second was we had to know what meters were connected to what transformer, because if that wasn't accurate, then all the calculations were out the window, right? But fortunately, we have a very accurate GIS system because we invested the money to get it that way. So because we had these 2 pieces, we were able to build the software. And what I'd like to do is just really show you a brief demo of the software and really the power behind it. So the screen you're looking at here is the executive kind of snapshot of how the system is performing at all the different levels. And if we go into our transformer loading tab here, now what you're looking at is really the combination of all of that GIS data, our mapping data, and it's our entire electric system mapped on top of a Google Maps background.
1 second. We're hitting the 11 o'clock hour, so we usually ask the council members, are we okay continuing? Yes. Okay. I'm sorry. Go ahead.
Oh, no problem. So that map you're looking at is really our entire electric system. And all those green dots, if you zoom in, every green dot you see on that map represents one of our transformers. So now instead of having to manually extract all that data, this software actually, every day, it imports all that data, so we just have it at our fingertips. And the power of having all that data at our fingertips for every single meter means that we can see the system in ways we could never see it before. On top of all that other research we've been doing with loss of life and total owning costs, now we could look at the system in different ways. So let's say, for example, we want to look at overloaded transformers, the ones that have high risk of failure. Let's say everything above 170%. So now it's really as simple as typing that number in, and at the click of a button, the graph change, or the map changes. Now all those little red dots you see are transformers that have gone above 170% of their capacity. These are all transformers with high risk of failure. And this was really the game changer for us, because we could never see our system this way. Now, by being able to pinpoint all the weak areas of the system, this really allows us to make better decisions as a utility and really improve our reliability. And if we wanted to look at any one of these, we could just click on it now instead of having to go through all the crazy spreadsheets. Now, at the click of a button, we can see that same information and do our analysis. We could also look at the same thing in a table view. And why do I point that out? Well, because in table view, it's a sortable table. And sortable means now we have a priority list. We have an actual priority list for these pieces of equipment in our system, something that we've never had before. We know what the worst performing transformers are, and we can work down that list and make sure that we fix them before they become a problem. And a recent success story I just want to share here is that last September we had our major heat wave. We had multiple days over 100 degrees, and heat waves, this is actually a major heat event for us. It means it reached some records. So in the electric industry, that wreaks havoc on our systems. Transformers are failing, fuses are blowing, feeders are going out, there's outages. And really, this is where you get to see how well your system was built. This is where you get to find all those weak points. We estimate as best as we could and tried to build our system as well as possible, but really, we had to wait till major events like this to see where the problems in our system were to go and fix them. We don't have to do that anymore. I showed you that map with all the problem transformers. We in Burbank, since March when we installed the software, we worked down that list. And we took all the transformers that we predicted would fail, and we released work orders to make sure we go out and replace them or adjust them. And unlike all of our Southern California neighbors, during that heat wave, the number of outages for transformers in Burbank was 0. 0. That's unheard of in the utility industry. I mean, to have 0 transformer outages during a major heat event like that is really almost an impossible feat, and we did it in Burbank, and something we're very, very proud of. So to sum this all up, we, the utility business, we spend every day trying to make sure we run the most efficient system possible. And the driver behind that is really customer service. We want to make sure our customers are getting the best power they can get. And because of all this predictive analytics, now we are helping them reduce the number of outages we have to see, unnecessary outages, which means, in the middle of the night, our crews don't have to roll out on overtime to fix a transformer that doesn't need to be fixed because we knew about it already. On top of that, we don't have to estimate anymore. Those days are over. That era is left behind. Now we know we have all of the data we need to analyze our transformers in ways we never could before. And that's really going to help save us a lot of money in the long run because we're making sure we're picking the size that's just right. And really what that means is we're balancing maintaining reliability now with managing cost. And I told you we spent $70,000 on this software. Since March, because of avoiding those outages and making sure our transformers are sized correctly, I would argue that we've returned our investment a couple times over in less than a year. So in closing, I really hope I've shown you that we're changing the game in Burbank, and by being able to use all that data in ways we never could before, that like other utilities are looking to us to see what Burbank's doing now. And really, we're able to see our system in ways we couldn't before, and it's really helping us maintain our reliability. And really, just in closing, this is just the tip of the iceberg. Predictive analytics is just the tip of the iceberg. And really, I was glad to be a part of that project, and I really look forward to what's to come for Burbank. So with that, I'll take any questions.
Thank you. Councilmember Talamantes.
Thank you, Mr. Mayor. Thank you very much for your very enthusiastic report at this late hour. But you mentioned the fact that you can either go out there and replace them or adjust them. So transformers can be adjusted?
When I say adjust, I mean sometimes you might have 12 houses on this transformer, and the one next to it you might have 8. Sometimes we can actually just move where the split of the wires are and just move it around, and that bounces the 2 transformers out.
So lowers the power on one and
Exactly.
kind of shares it with the other one. And who else is using this?
We are the first utility that has this fully implemented, this particular software. And really, to our knowledge, we're the only ones that have 4 years of data in our AMI system, a great GIS system, and we're able to use all that data in a software like this. The company that partnered with us just wanted us to do demos all the time for all other companies across the nation because we're really the first.
We got into the $70,000 level.
Yep.
I'm sure it's increased quite a bit since then.
I'm pretty sure it has.
Anyway, thank you very much for your report.
Sure.
It's very interesting.
Vice Mayor Prudhoe.
For bragging rights, I'm on page 4, electric reliability. I noticed that you said the probability that Burbank would have a power outage is like 1 in, 5 years?
1 every 5 years, yes.
And then I'm looking at the scale you brought up, and Glendale is at 1.0. So it's kind of interesting how our neighbors to the south, obviously they're not as good as the Burbank Water and Power Department. So I just want to make a comment. I'm really glad to see that. So next time I see those other colleagues there, I'm going to brag about our reliability of our utility. Thank you. Good presentation.
Of course. Councilmember Gabaldini.
This is a great application of analytics. And I guess this is the next step out of having installed the smart meters with the grant that we got, 3 years ago.
Exactly. The fact that we can gather all that data means we finding ways to use it every day.
It's a brilliant application. If we're third out of 223 utilities in reliability, I know I looked at the recent report and it's 99.9925% reliable for this utility. And I would extend my compliments to everybody who works as a team at BWP because this is clearly a very impressive result. And then I guess the last question on analytics is, can we adapt this kind of analytics software program to other things in our city that require regular maintenance? Like, how about all the drinking fountains? GIS, we know where they are. We know the size of the pipe that feeds them. Maybe there's a way. I don't know, but,
How about duration?
Seems like
I think
the sky's
anything is
the limit.
possible.
Good idea.
Very good report.
Let's put that
Thank
in.
you.
Congratulations.
Thank you.
Let's put that in play.
I have a quick question. On page 12 of your graph, you have the 25 kVA, 37.5 kVA, 50 kVA, and 75 kVA with adjusted lifespans of 12, 35, 40, and 40. And the costs are going down from the 25, 75 until you get to 50. Then it sort of optimizes cost of 305 per year. And then it goes up again. Why is that?
Why does the last one go up again, the 75 kVA? Because it equates to more cost, and it also equates to more losses over the time that transformer is up there. So if the transformer is too big for the load it's serving, you're going to waste energy, and that cost gets factored into the lifetime.
You're optimizing the size optimization.
There's a sweet spot that we try to find.
And then the question is, you buy these light bulbs and they say they last 1,000 hours or 2,000 hours, 20, whatever term they say. I never know how accurate those are. I'm assuming they're using the old estimate system. How precise are the decaying of these transformers based on your temperature factors or utilization? Are you throwing away good ones? Are you replacing ones that really have like 5 more years, or are they really down to like 10 minutes before you replace them? I mean, how precise is the deterioration of the transformer?
It's very precise. I mean, it's down to minutes, basically, where we can predict how much this transformer has degraded. Now, there obviously may be other factors, but that's going to be a question we have to now tackle is, when do we actually replace this? When it's reaching the last minute of its life or before? I mean, those are questions we're still asking ourselves. But it is very precise, all those calculations.
Okay, and so the plan with this predictive analytics is to replace these prior to failure?
Correct.
Just prior or reasonably prior to failure?
Well, each year, last year we got our list of ones that we predicted that would probably fail during the summer, and we replaced all those. And each year that's going to change. So each year we're going to have to look at our list again and analyze and predict which ones are actually going to fail, and that's the ones we'll go out and replace.
Does your information tell you if certain locations of transformers need to be upgraded to larger ones or smaller ones? Can you tell by the utilization what size transformers need to replace, or is it you just automatically replace the same size transformer?
Oh no, this software allows us. I didn't take you to the other tabs, but there's a whole analysis tab where we were going through all these equations before, and we can run what if scenarios, and let's say we put a 50 up here and see what happens over the lifetime. We can do that with the software too.
I see. Okay. Well, I would echo the comments of the different council members that this is really, really an excellent report. It's very encouraging, and hopefully you can continue preventing segment down in the budget time the cost savings from this program, because it was a big investment.
It was.
It was, of course, grant funding, but it's still money. So it'd be interesting to see how the savings can be documented over time. Perhaps that could be brought forward when you bring your budgetary calculations. Councilmember Ghiberletti.
Mayor, I'd like to encourage this presentation be made to our Chamber of Commerce. And I think that they would really appreciate seeing the extent to which the utility is continuing to be a nationwide leader in the application of new technology.
I don't see why not. We have our monthly meeting coming up. I don't know. I don't know what your availability is, and Mr. Davis, I'm sure this is good stuff. In fact, we're going to be talking soon because you guys are on our list for one of the mayor shows. But this would be good stuff to put out in that regard too. But I think we can coordinate with Mr. Scott and the Chamber.